Okay, good afternoon. Thanks everyone for coming. It's a real pleasure for me to introduce our speaker of today, Professor Ekhard Salje. He's professor of mineral physics in the Department of Earth Science of the University of Cambridge since 1992. And he was the head of this department during 10 years in the period 1998-2008, if I read it correctly. Among many other awards, he's a fellow of the Royal Society. He has the Order of Merit of the Federal Republic of Germany, and he has the Ising Prize for Physics in 2002. Just as indication of his prolific career, he has an H index of 66 in the Web of Science. It would be difficult to summarize his different research achievements, but perhaps I can summarize by saying that he's the world leader in applying physics concepts and methods in mineralogy, and most notably concepts of statistics and statistical and nonlinear physics. He's been very active in recent years in avalanche phenomena and stochastic processes in this phenomena. And I checked today in the Web of Science, his most recent paper that appears there, at least, is in Physical Review X this year on global formation of topological defects in multiferroic hexagonal magnets. So it's a pleasure to have you here. Please.
I use this one.
No, it's okay.
All right. Well, thank you very much, Maxi. I must say it's not the first time I'm here. I've been here many, many years ago. And Maxi was so kind in those days to show me the University of the Îles Balears. And it looked like Heathrow, the landing plane, you know, where they come down. There was one building and the rest wasn't built yet. So you can imagine how long that has been back. Now, I'm here in Kalmar to work in the physics department with Sergio Christoph, who is not here, but he might come at some point. We are working on friction, and it's quite interesting when you go to a university. You know, there are well-established groups like the group you have here, brilliant. But there are sometimes some pockets of people who do things which were very popular 20, 30, 40, 50 years ago. And because everybody else got out of the field and they stayed in the field, they're now the world leaders. And not only are they the world leaders, the subject had actually turned back to what they're doing. And suddenly you can do things, in particular here, I mean, I should tell you, you have the best lab in the world to measure nonlinear fraction. There's no other lab in the world doing that. There are some Russians somewhere in some area where it's very cold and you couldn't go there. But so that's why I'm here. Now let me introduce what I'm going to talk about. I want to talk about complexity. That's one of the key things we are interested in, not only from an earth science perspective, but also chemistry and physics and mathematics. And one concrete way of making use of this concept here is domain boundary engineering. Now, I should start by saying the materials I'm looking into are basically ferroelastic. Ferroelastic it has a strain stress hysteresis. And in your mind, I mean, if you have never seen that, don't worry. You have certainly seen ferromagnetism, and you have seen ferroelectricity. Now, ferromagnetism is a bit more than 100 years old. Barkhouse is 101 or 102 years old. Ferroelectricity is about 50 years old. And ferroelasticity, seriously, is only 20 or 25 years old. Now, this one is by far more common than the other effects, but it has been considered, at least in the physics community and engineering community, as extremely boring. Now, why is it boring? You can't make money with it. You cannot produce a device which is ferroelastic, because what it means, you have a ferroelastic, it's like a switch. You have something, you switch, you tick it on, it goes like this, you tick from that side, it goes like this. And you can do that as often as you like. It's basically a switch, and that is what this history is about. Now, I will tell you why it's not that boring. In fact, now, ferroelasticity in the last 2 years has become even more popular than the other two. And there are more people working now in this field. And when you look into citation and so forth, this one is a runner. But I will explain why that is the case. Now, that's why I call it engineering. It's just a quip against the engineers. So, we know exactly why this happens. We know atomistically there are some atoms switching from one position to another. It's the usual multi-valley behavior, so that's quite well understood. But I want you to here's a lead atom which has a lone pair electron. It depends where the electron sits. Now the switching atomistically is just a little bit more than the thermal amplitude, right? So you're talking about a fraction of an angstrom. I mean, normally 0.02, 0.03, 0.04 angstrom. Very, very small. Macroscopically, on the other hand, this adds up. You have many atoms, right? You have really quite a massive deformation, and the strain here, as you can see, is in the order of a degree. Now, what is much more important, and that, I mean, this picture comes from 1992 when the first big effort came, and I wrote a book on that, not knowing exactly what we know today. I mean, otherwise I would have written it quite differently. Now, what you find here is this material is a monocrystal, this area is a monocrystal, but everything in the interesting area is not a monocrystal, but it has domain boundaries. And it has domain boundaries which are related to twinning. So you have one a bit sheared that way, a bit sheared that way, a bit sheared that way, and so on, right? It's like ferromagnetism. You have magnetic boundaries. You have electric boundaries. Now you have elastic boundaries. But these elastic boundaries are, if you look as a geologist at the surface of the Earth, it's about 60 to 70% of all material on the surface of the Earth have this effect. And the influence is seismic influence also. Now, engineering-wise, you have in this area parallel domain boundaries. Here you have also parallel domain boundaries, but in a different direction. And here you have domain boundaries which intersect and do all sorts of funny things. Okay, that's all what you need to know about this one. Now the big discovery of a domain boundary engineering, this one, was functionality. So why do we have these boundaries? Is it just to annoy us, to make things difficult, or is there actually some good stuff about it? Is there some chocolate in there, right? And the answer is yes, it is. And that's what we call emergent functionality. So if you read papers in PRL over the last 2 years, always this emerging functionality. What it means is the following concept. Here you have a picture of these domain boundaries, okay? Then you magnify what is here, and then that's how they geometrically have to look like, because you have something in that direction, you have something in that direction, in the middle you have a different unit cell. So the atoms have to arrange themselves somehow to fit into the pink area here. Now what you immediately can say is that these ones are rectangles and these are kite-shaped. So there, if there's an atom in the middle, there's absolutely no reason why it should move anyway. I mean, all directions are almost isotropic. If you are here, then you can clearly see there's a bias in this direction, either up or down. Either the atom is too big or it's too small, but it doesn't want to be in the middle. And that's what it is. It doesn't want to go right or left because that's symmetrical. So it's just very simple symmetry argument. And now you have two things. You have intersecting domain boundaries, you have a phase transition, so you're nonlinear, and you have choice. You can go up or down or something like that. And that together defines a complex system. Complexity is defined like that. So we have a complex system. And the question is, what does the atom do? Now, what we predicted and what we know now, but only since the advent of the new generations of electron microscope about 2 years ago, is that these atoms indeed are not in the middle. I mean, we were talking about it until we were blue in our face. But of course, we couldn't prove it. We could do DFT calculations. We could show the energy minimum is not in the middle. But if you can't show it, nobody believes you. Now we know that all these atoms here, these are titanium atoms, are not in the middle. They're in the middle here and here, but not in the wall. So the wall has therefore dipole moments, polarity. If it has polarity, you can put a field on and you can play with it. So you can reverse them, you can tilt them over to that side, tilt them over to that side, just by an external field. Very small field. We're talking about a few volts here. Very small field, not big fields. And that means you have a memory device. Right? Now you can see the dollar signs in all the research councils. You know, they say, hey, that's an application, and the administrator will become famous for that. So that's how it works. So what we can do with these emerging functionalities, in this case the polarity, is to build a memory device. And we can do that. There are some around, ferroelectric functionality devices in Japan, and these things by now exist, and lots of companies are working on it. Just to show you for this material why that is the case, again, the unit cell is different. In the unit cell, you have a few octahedra. These octahedra are all tilted against each other. That's what perovskites are supposed to do. And then the key on that is that when you look inside the octahedra, you have titanium. Now, if you know a little bit of chemistry about titanium, lead, all these materials, if you have an isotropic surrounding of oxygen, so negative, then you know that these atoms don't want to be equally spaced to all the others. They hate it because they gain energy by going closer towards one oxygen, gaining a lot of energy, and losing a little bit of energy to the others. I mean, it's this off-centering thing of titanium. Now, it's very often related to the fact that they have a lone pair electron, they're D systems. I mean, there's a lot of quantum chemistry, which is textbook stuff, which tells you that that is the case. Now, in fact, for ferroelectrics, almost all ferroelectrics, not quite all, but many of the ferroelectrics are titanium-based for this. So that's known. That's not me. Okay? So, but you can see it goes outside. But then you have to ask yourself, how do they do it? Are two neighboring going the same way? Are they going opposite way? And so forth. If they go opposite way, that's bad news, because then the net effect, of course, is zero. You go up, down, up, down, up, down. So what do? You know, choose another area. But otherwise, you can't do very much. If they go in the same direction, then it's good news. And so here are the simulations, and you could say in first instance, that's bad news because they go up, down, so they are opposite. But you can see there's a drift to the left, and we're only talking about the drift to the left, which is the real functionality. The big one, up, down, is not so important, at least not now, because we don't know how to master that. But the other one we can. So then you look in a bit more detail. And here I want to show you that you don't see anything. Well, do you see here is a funny line? Can you see that from the back? It's a bit darker, isn't it? That's the twin boundary. That's all what there is. If you look at an atomistic level, this stuff and this stuff the same, and this dark line here in the middle, which only a few atoms take, that is where the action is. So, I mean, they're different depending on your taste, how you want to describe it. You can describe it as a sandwich. You have a lot of bread on one side, a lot of bread on the other side. In the middle, a thin layer of meat. But that's an English sandwich. The sandwiches I've eaten here, they're quite different. So that's perhaps the wrong. I mean, other people say this is vegetable and that's the main course. Whatever you say, but you see the emerging functionality is localized. I mean, it's really localized in this thin layer. Now, what is important to get into the back of your retina is that the thickness is really 1 atomic layer, 2 atomic layer, not more than that. That means a device for instance, for a memory device, for a computer, is only 1 atom thick. It's not 100 atom thick. It's not 1,000 atom thick as it is now, right? So here is the next big step, how you can scale down. You can scale down by not making device smaller and smaller, but to have an internal structure inside the device and only using the meat, only using the emergent functionalities and forget the rest. The rest is really only vegetable. It's only there to keep the thing where it is, right? So, and then if you go to high resolution, that's again the thing.
Can I go one back?
Yep, sure.
So, what's that square there on the right up there?
Oh, that is just to show when you do a fast Fourier transform forwards and backwards, you end up with the same. It's just a reality check that you're not cheating. So here, that's now a slightly higher resolution, and the white spots are indeed the titanium, and you can see that's the pattern. So all the pattern, all the titanium go in that direction. There's a relaxation going in that direction, and so forth. I mean, how the exact pattern is not important for you, because we have several materials now which can do that. But the importance is there is a dipole. And so this race started 2008. 2008 the idea was published. And then this one was done 14. So it took a few years to get the electron microscopy going and so forth to come to this one. But now there are more and more materials doing that. And you really go through complex materials to see where that is. You can't do it on sodium chloride and so forth. But you have to be very careful that it's only the nano-structure inside the big structure which is the carrier of the information. It's not the structure as such. And so when people in the past, they measured this stuff and said, is there piezoelectricity? Of course there's piezoelectricity. You can see it here. That's why there's piezoelectricity. But they couldn't measure it because there are very few domain boundaries, and therefore you have such a weak signal, it's within the noise. So you forget. So you have to think how to measure it properly and what methods you have to use. Now I like small experiments. In particular, my size discrimination thing is if I can put an experiment in my pocket. And this one is a pocket experiment. I mean, this one, that's about the size. And so it looks really quite primitive, right? I mean, it's almost for mathematicians, something like this, right? So what you do is you have here a crystal, I mean, a holder, and you stick on with glue. Here's the crystal. And then you poke the crystal down and shear it and see how these functional interfaces are now moving, because you can make them move, because twin boundary can move. So now it's actually not that stupid. This is intelligent because this bit is intelligent. That's for soft matter physicists. They know what it is. I mean, it's a soft plastic which you compress, which releases the pressure over 24 hours, very slowly. So when you push it down a little bit, you touch it. So you compress these bead, the round thing, and then it expands over time and increases the pressure linearly. All right, so it's not a stupid device. It's just small. So then you look at it, and so you create a domain boundary, and this domain boundary is now going forwards and backwards. I will show you later a video. Right? So you see they're actually themselves also quite complex, because in textbooks they're always parallel walls and everything is fine and so forth. But you are strained. I mean, your material is deformed. And so these ones have to follow the energy minimization, but of the deformed area. And if it's deformed, then you see that these lattice planes are actually no longer parallel and so forth. Now, if you look at that, this one's actually from a photograph. So here are straight walls, and then the needle tip comes in here, and FL means front line. That is the top thing which goes forwards and backwards. Okay. Now immediately you come up, I mean, if you have an inkling for theory, you say, my God, this one is fine. That's an energy minimum. this one is a bit complicated, but okay, you can imagine you write down a complicated equation, you will get then a solution simply by having nonlinear elasticity, so that's easy to understand in principle. But what the heck is this? Why is it not straight? I mean, your energy goes to 0, and then it should be straight. But it isn't. And in all these experiments, it's not straight. Now, of course, there are intelligent people around, like Larkin. He already sort of, I don't know, he's dead for a time, so I don't know how, when he said that, but he said this one has to be wiggled, and then the length scale of the wiggle is called the Larkin length. And if you go to complex systems who look into these problems, like the Imperial group, they work on that, Janssen, and there are lots of people looking into that. They want to know what is the Larkin length and where does this come from. And of course, it comes from defects, or it comes from heterogeneity. So if you propagate something, the heterogeneity which you sweep up adds up. So you start with something which looks quite reasonable, namely straight, and then the more you go out, the more jagged it becomes. And there are specific rules for that. And well, let's see whether I can get that going. Oh, sorry. Did that move? No, it didn't move. Yes. Ah, now it moves. So that's how it looks like. I mean, it's a high-speed camera, but in fact, this experiment takes about 24 hours. So we make lots and lots of frames, and then just edit it in such a way that we cover the 24 hours. And what you can see are these needles I was just talking about. They're shooting in, and then for those in the trade, you see immediately that you have secondary needles which are perpendicular, and then you have tertiary needles which are there, and quaternary needles, and so you have really self-affine.
What is the size?
The thickness of the wall is about 2 angstrom, and the this size here is macroscopic. I would say 5 micron, something like quite standard. And you know, so you can make them. Now, what is important is that because you can make them, and you piggyback the functionality on them, you can make an entire computer chip. This is the way to make a computer chip, if you want to. Right? So you make the lines where your electrons have to go in the end, or whatever you want to do, by squeezing something mechanically. Then you have these things, and then like in a photographic process, you put in the functionality. I mean, it comes automatically. You don't have to do anything. And so wherever a boundary is here, like this boundary here, okay, that one has the dipole moment. And so you're pushing dipole moments around here. So this one is already, if you like, a production process. But they minimize the elastic energy. And just to show how much you can do there, here this is exactly the same crystal, just rotated by 5 degrees and doing the same. And you can see the pattern in general is the same. I mean, they shoot in there. But the ratio of the primary and secondary and so forth is totally different. And you have lots perpendicular here. So which is, you know, if you calculate the elastic energy, you can see why that is the case. I mean, I'm not saying something entirely new here. We know which pressure gives which microstructure. But in reality, you can do that. And you can do it dynamically, and you can stop anytime you like, and then you have a pattern. And this pattern has now the functionality, because the walls have the functionality. So that's the concept. That's the domain boundary engineering. So, and every step, we do it in an indirect way. We are not making MBE thin layers where we put something in here and there and so forth. We take the final device, we structure it like this, and then the functionality comes automatically. Now there are a number of interesting aspects here, but it's probably, well, let's see how it works. So this one is one of these domain boundaries going to the surface of the crystal, which is here. And the slightly lighter one is where the domain boundary is. Now, you all know pinning. You have heard about pinning. So if there's a defect, there's a surface, it gets in there, it doesn't want to go away from it. I mean, it's just, it minimizes the energy, and so if you go away, you have to pay energy to do that. Now what you can see here is what the surface does to you. It's very interesting. Here's the surface. And now here it has already been stripped off. We have forced the boundary to go downwards, but this part here is still pinned. And here's the line, the front line, which this one has to be there, and it wants to go down. Then you increase the force, and you can see this pinning area becomes smaller, and this one gets longer, and then blanc, it comes off. And now it can move fairly freely. So surface pinning can be observed in these systems directly. You just take a photograph. And again, you can then look into freely moving ones which are not pinned. And then you can see here's a scratch on the surface. The scratch on the surface they recognize. And then you get more complicated pattern there. And all these then have, if you take the autocorrelation function, it looks like this. It tells you what the larking length is. So now you know that a freely moving front line actually is structured. A front line is not a meniscus or it's something, like in fluids where everything is honky-dory. It's not here. I mean, it depends on the defects you have and then that real microstructure and so forth. And it has these oscillations in there with a characteristic repetition length, and that's the larking. So now you know what the larking length is. And this one, I should say, is the only time a larking length has been measured precisely. I mean, all the rest is sort of computer simulation and stuff like that. This one here you can see, it's not a problem. You can also move in another direction. You can say, all right, we can make these domain boundaries. Why don't we make more and more of them? Once you know how to do it, why not making more? And if you make more, then you bump into what we call Tween structure. That's actually something we discussed 100 years ago. Right? 200. So you see here are the domain boundaries, but here are areas where everything intermixes. And it's a different thermodynamic state. I mean, it's a fluctuation state. But the fluctuation state can be created against by external stresses and stuff like that. And then, so, I mean, Tween was known. I mean, there are about, I would say, 200 papers on Tween. They're known. But the question is, what is the functionality of the Tween? And now we know because walls, they're tiny little walls hidden everywhere here, they have functionality. Tween has functionality. So what you do then, you do a PFM experiment, and look for the functionality, and then you find it, which is not surprising. But first you have to understand that you have to look for functionality in these materials. Actually, the first experiment in the field which was ever done was 1998. I mean, it really started with that experiment, which I did with a student from Glasgow. Very nice lady. The only problem was she was from the inner city of Glasgow, and as I'm a foreigner in every country, I couldn't understand her. I mean, whatever she, and so she's English, I mean Scottish, and so we had a piece of paper and we were always writing down what we were saying because we had the same language in writing, but we couldn't understand. And then she became a patent lawyer because she said science is too exciting. Okay. So what we did is we took, this one is just a more modern version of it. So here are the domain boundaries. That's the topology. Here is the conductivity, and you can see the domain boundaries are also more conducting. So you have a wire automatically, a wire in there. And this one is the piezo effect in tungsten oxide, it's a different material, where it's the other way around. This one is polar, but the boundary is not because it's so highly conducting that the piezoelectricity collapses. Right? You can't have piezoelectricity in a metallic material because the electrons will compensate for the dipole moment. So there is no dipole moment. So here you can see that in the PFM signal you have black for the boundary and for the current you have white. Now what is very interesting is that this white is really very white. The conductivity on tungsten oxide is a good insulator. Think of sodium chloride, it's when that leaks. really a good insulator. These conducting areas are like a metal. So you have like metal planes in an insulating matrix. But it gets better. When you go to low temperature at 3 Kelvin, these areas become superconducting. So now you have superconducting planes in insulating material. Right? So that's quite spectacular. And of course, what you can do, what we have never succeeded yet, because it's too much work and we are not equipped for that, is to, I mean, these are Josephson junctions here. You can make, for instance, brain scanners out of that. I mean, you know, if you want a brain scanner, then that's the way to do it. So, or you want astrological or astronomical devices for measuring sort of solar winds and stuff like that. You use Josephson junctions for that. And here you have a very dense array of Josephson junctions, which are sort of God-given. You don't do anything to that. I mean, you trim the materials heavily, then you get these superconducting bits in here. They form Josephson junctions amongst each other, and then you can do whatever you want to do. Another area, I mean, I want to give you just a flavor what you can do in this field, is nanowires. It turns out the smaller the material is, the higher the nonlinearity. I mean, that you know. But if you take a just good old iron, and you have to make it a bit thin. I mean, you make a nanowire. And then you do the following trick. You take the wire and you twist it. Okay, the nanowire is just nanowire. I mean, it's easy. But when you twist it, then of course you want to introduce dislocations. You have to.
Is this a hollow nanowire?
Yeah, it's a hollow nanowire. And when you twist it, then you get these dislocation stuff in here. But the blue stuff here, which comes after some while, if you have twisted enough, are twin boundaries. Right? It's just the atomic configuration of what you create by twisting is again the twin boundary. And now, of course, here we can't have polarity because of the metal or whatever. But if there is polarity, then it will be in the blue areas here. So that's one part of research which is particularly done nowadays in China, where they take nanowires of all sorts, twist them, create these functional elements in there, and then test whether these functional elements can do something for you. They are either polar, they conduct differently, they whatever. Right? So that's part of it. Now you can, of course, I mean, I said before, if you test material in the classic way, you always test bulk material. I mean, that's how we were all brought up. If you have something you want to know what the structure is, you X-ray it, or you do neutron scattering, or something. You do something macroscopic. Now, these days are over. For this one, we can't do that. Because the bulk, the massive part of the sample is vegetable. There's nothing there. I mean, it's all the stuff you can read up in books. Nothing, right? So what you have to do is to excite the stuff which is functional. And one way of doing that, a very simple way, is to take a sample which has supposedly something in there which is polar. And then you put a very small voltage on it, very small, 10 volts or something like that, a macroscopic sample. So not ferroelectric or something dramatic. Now, if there are domain boundaries which are polar, what do? You shift them around. You swing them from right to left. So then, you can't measure that, of course. I mean, in an electron microscope or so, you can't do that. But what you can do is the emitted sound. You move them forwards and backwards, and then you measure at these two ends, you put some sticks on there. I mean, these are ceramic sticks. And then you put at the end of the stick a microphone. Well, it's a glorified microscope. It's a very expensive microscope, but it's still a microphone, but it's still a microphone. And that gives you on your oscilloscope. Now, if these guys swing all in phase with a nice big amplitude in resonance, then at the resonance frequency you get crackling noise. You make brrr. It really sounds like that. So when you go there, brrr, depending on where your frequency is. Okay? So that's a testing way. So you're not testing whether the material is piezoelectric as a bulk material, which would be very easy. You just squeeze it and you measure your voltage. But you have to go into the resonance of the swinging interfaces, and when the swinging interfaces swing, then you get a macroscopic signal, which is an acoustic signal. So you transfer from the electric signal to the acoustic signal. And that's a highly, highly sensitive way of doing that. I mean, with this one, we can about 4 orders of magnitude more sensitive than a bulk material. And the interfaces are about 4 orders of magnitude less material. So, I mean, we are in a similar ballpark of sensitivity. And just to show that it works, here are these resonances in strontium titanate, which is not quite a War-ring material, but it's not polar in principle. The material is not polar. Here's the phase transition in strontium titanate, and here's the resonance frequency, which changes. And then at low temperature, you can suddenly see there are all sorts of peaks coming up in a very complicated structure. And that is when these interfaces suddenly become polar. So at high temperatures they're not, at low temperatures they are. And, you know, so that gives you a few PRLs. You can also simulate that, of course. Again, the interface, here's a simulation of strontium titanate, these tilted octahedra. Here you tilt in one way, here you tilt in another way, and here's the twin boundary. Because they have to tilt to the right, they have to tilt to the left, and when the two come together, they can't tilt at all. They're stuck. It's a wrong structure, basically. And that's the thing of the functionality. The functionality comes when you have the wrong structure. And in a twin boundary, you always have the wrong structure, because you can't be right and left at the same time. So you have to combine these two to some new structure. And the new structure can have all sorts of things in there. And so here, this one would be the untilted octahedra in strontium titanate. And that is the area where the dipole moment comes. And then if you take an interface between strontium titanate and aluminium oxide, lanthanum aluminium oxide, you get these free electrons. So if you now smear free electrons on top of it, and you do an AFM experiment where you squeeze the entire device up and down, suddenly all the domain structures of strontium titanate come out. I mean, it's like a photographic process, really, when you look at it. I mean, you have this thing, and you don't squeeze it, you don't do anything, it looks perfectly. It's totally uniform. And then you squeeze it at some point, and you just measure the conductivity in a 4-probe experiment, then you suddenly see all these microstructures. So it shows that these microstructures per se are the consequence of the complexity of the material, because it's highly nonlinear. You have the choice between going right and left. Then you can't go right and left. You have to compromise somehow. You create something new. That's a complex system. But then you can make something out of it, because this complexity then will lead to these microstructures. And the microstructure on top of it have these emerging properties. And then you can go from there. Now I want to say a few words about the dynamics, because Maxi already said I got recently quite fascinated about avalanches. I'm a lousy sportsman. No, 50 years ago I was quite a good sportsman, but that's gone. So I can't ski or anything of that, so avalanches in that sense are of no interest to me. But if you go through these phase transitions, again, I mean, it comes really from the domain boundary engineering. We learned that the classical measurement techniques which we have developed over 100 years, you know, measuring specific heat, stuff like that. So I went to friends actually in Seville, you know, Carmen Gallardo. So they have means to measure specific heat over very long times. So here is a specific heat peak, which when you go in a DSC or something, you see a peak. You know, what you learn in physics when you do that sort of thing. Now, or not. Now, if you measure that now over a period of 1 week, it takes you 1 week to go through the peak. That's technically not a problem. You have a computer. It does it for you. You go to the beach and come back. You're not doing anything. The best is actually to be away. Otherwise, you will influence the experiment. So leave it alone and just run through this temperature interval here very, very slowly. Then, of course, you will find what you always suspected, that the peak isn't a peak. Because why should something go from A to B, structurally change? It doesn't. I mean, it takes bits which change quickly, and then another bit changes, another bit changes. But it's never that it continuously changes from A to B. It just simply doesn't happen in nature, and it shouldn't. I mean, otherwise thermodynamics would be wrong, or statistical mechanics. And so if you then do that very slowly, you find that this peak actually, or when you stick it together again, is actually time-resolved, a series of steps. And each step is an avalanche. It's called the crackling noise. And since 2002, crackling noise is very trendy. So one wants to know more where these crackling noises come from. And here they are. I mean, crackling noise up and down. And we just wrote a book on crackling noise in functional materials, so what I was talking about, and geophysics, because after all, I'm in a geophysics department, or geology department, or earth science department. So in these two areas, it's predominant. But what probably most people do now is biological. They take neural networks. They take a fish, where parts of the neurons lit up when the fish stinks or whatever it does. And you poke the fish with a needle and say, ah! And then these neurons lit up, and you measure that over a period of time, you get the same thing. And so these are these avalanche neural networks, and they are all over the place. Now again, my pocket experiment. And this pocket experiment is not in my pocket, it's in Tony Planer's pocket in Barcelona. They have built this a long time ago, but then now it's becoming really very dominant. So, because the new materials are there. So what you have is a holder which hangs on the ceiling. I mean, this one is very small. And here's a sample. And then you have a second one which you pull down. So basically you squeeze the sample. The trick, again, from all these things I'm telling you, is to be as slow as you can. Okay? Siesta time. Not doing anything. It's the best. So how do you make this one slowly going down? Well, in Barcelona they found the answer. They found an old bucket, hang it up there, and drip water into it. And you can drip the water as slowly as you want. And so experiments of that kind, I mean, they take 2 days to fill the bucket. But it's about that time, but you could go even much slower. And now the Chinese, of course, they built the same machine from a press which where you can put a car in their form. I mean, it's a huge thing, and they drop oil into it. So it's the same, very similar. So what you do here is you have a very slowly increasing force, which gives you a stress on your sample, and then you measure how the sample collapses, or what the sample is doing. So here is this high-tech nano-porous Y-core. It's basically SiO2. It has a porosity of about 40%. You can make different Y-cores, and it's used for filling of aircraft wings inside. You need light material, which is quite stiff, and we want to destroy it. Okay? So we squeeze this one, and then one pore will collapse. It's linked to the next pore, which will perhaps also collapse. And then there's another one which might collapse, depending on the coupling. And then there's one, because it's a non-local phenomenon, at the edge of the sample, which then, by sympathy, also collapses. And, you have these networks, these collapse networks. And then each time a collapse, I mean, a collective, an avalanche, I mean, the collective thing is the avalanche. So if one of these avalanches happens, you find an acoustic signal, exactly in the way I showed you before. And each spike here, which we call a jerk, each jerk is an avalanche. And you see we have about 20,000 here. You only see the big ones. There are loads and loads of small ones in here. Right? Then you put that on a computer. Today's computers are cheap and powerful. So you put all this data on the computer, and then you take the probability distribution function, which basically is you bin it. You take lots and lots of bins, and then you say which signal is that bin, which is in that bin, and so forth. I mean, that's automatic process. And here's the energy of the avalanche. And you can see, first of all, we are talking about 6 orders of magnitude. Now, 6 orders of magnitude is not a triviality. 6 orders of magnitude is a lot. If you go 10 to the minus 6 meters, that's pretty small, right? Or you go up from 1 angstrom, 6 orders of magnitude big, it's quite big. So, you know, you have a huge range here. And the probability function here, theoretically, should be a power law because it's scale invariant. And you see, it's a power law. And the exponent is 1.39. And as you know, the theoretical value for mean field is 1.33, 1.34. So we are basically a mean field type of behavior, but over a huge range, huge range. And, you know, that is really, really new. Because a few years ago, we could do that on 100 data points or 500 data points. Nowadays, you know, if we have less than 10,000, then my students say, oh, I can't do that. It's nothing. Right? So we have very, very good data, large data sets. And if you can work with these large data sets, you get fantastic data. Then you measure the time interval between 2 of these avalanches, and then you get, again, this one is the theory, and it fits the theory perfectly well. But what's more important here is, for fun, we have also plotted the same distribution for Californian earthquakes on the same scale. I mean, we have such a large scale. Why not to add a few 5 or 6 orders of magnitude? That's all. I mean, an earthquake is a kilometer. Kilometer is 10 to the 3 meters. We're in the meter range anyway. So 3 orders of magnitude to 6, nothing, right? So if you do that, then you can see the Californian earthquake data. It's green data, absolutely on top of this nanomaterial of Vicol. So the scale invariance really, really works. You know, there are very few examples in physics where you can go from about 5 angstrom to 50 kilometers, and the same physical law is still perfectly all right. And it's only in the dynamics, not in the static. It's not in, you know, of course, it all looks different. It's different processes. But scale invariant is scale invariant. And the dynamic is scale invariant. And that's what you see. And, well, there are loads of other things you can do. So you basically go to the geophysics community and you say, I want to tell you something, and they say, go away. And then you say, well, you have these funny things like Mori law, and, you know, for earthquakes, all these analysis tools you have developed, or in fluid dynamics, there are similar ones, and they say, well, I know that, still go away. And then you write a letter to a friend of yours in California, and say, oh, that's very exciting, come on. And you go there and talk to him. So well, anyway, that happened to me. We have then used, basically, we have stolen the ideas from the geophysics community and have used them for nanomaterials. And that nobody has done before, because there are different departments and the communication is always notoriously bad. So now if you actually put them together into the same framework, then you can see that it works. And here is a project I do in China, because they have loads and loads of mining accidents, particularly in coal mines. When does a coal mine collapse? It's an obvious question, right? I mean, there are lots of dead people in there when it collapses, and it happens every year. So the question is, can you develop early warning systems? And so what we do now is we put detectors in the coal mine, and then we are not measuring how loud the noise is which comes, because coal mines always make noise, crackling all over the place. But we measure the sequence and measure the crackling noise, the exponent, and when the exponent goes from 1.8 to 1.3, you run. So, I mean, so you can actually make a lot of stuff, all of this. And we are at the beginning, miles away. So here, coming back, now you are all complexity people. Now let me say how much, I mean, one idea is to boil down all these really complicated stuff to a minimum number of ingredients to make it still complex. And this one is my favorite model. It's called by everybody the standard model. Okay, it's my favorite model. So you have pluses and minuses. These can represent atoms. You have just simple springs. I mean, springs you had at school, harmonic springs between them. But you have an intelligent spring. That's the red spring, which we call a Landau spring, because it's a double weld spring. So this spring wants to be a little bit bigger or a little bit smaller. I mean, this bigger, this is smaller than the square root of 2. If it's a little bit longer, then you stretch this one and you compress this one. If you do that, then the entire thing is sheared in that direction. You can see this one is sheared. This one is not 90 degrees, right? It's a bit sheared in that way. But of course, it's a double weld potential, and therefore, whether you shear to the right or to the left, exactly the same. Okay? So that's it. That's all what you need. So again, I mean, let me go through my notion of what I call complexity. You have the nonlinearity and you have the choice in between. So nonlinearity in the potential, and you have the choice between going right or left or whatever. You have to make up your mind. You can call it frustration or whatever. So, if you do that, then you just go in thermodynamic equilibrium. So you take this stuff, anneal it for a long time, and then they will form suddenly lots of twins. So you have this one in that direction, that in that direction. Here's a twin boundary. And because you have pluses and minuses, it also gives you a merging dipole moment. Okay? So this model reproduces everything I've said. And that's work I've just finished with Max Stengel in Barcelona in, not the University Concejo, in the Concejo. Yeah, Bella Terra.
Material sciences.
No, he's physics. He's physics with Gustavo Catalan. It's the same. It's a huge new outfit there. So then you have, so now the question is, okay, we are beyond. And we don't want just to understand the emerging properties, but we want to see what are the deviations, because deviations are always exciting because there's something new coming. So you have these guys. You see here is a kink. And when you have a kink, then the dipoles form vortices. Right? We haven't put the vortices in. It's not us. I mean, the material puts the vortice in. So if you have a kink here, you make a vortex. You have another kink here, you make a vortex in that direction. Okay? It's quite understandable because these dipoles go to the right, these ones go to the left, and they have to interconnect somehow. But it's a long-range forces, 1 over R3 forces, which come for the dipole moment. So you get that one in. And if you make that a bit worse, so you get more defects in there, then you get all the skyrmions in and whatever. They come automatically. And then the question is, what can you do with that? It's a different question. But you see that the deviation from the ideal structure is very small as far as the strain is concerned, but you can see here the interface between the various parts are well defined. Yeah, and so if I take the relaxation of these things, then I can calculate the relaxation time, and what turns out is if you leave the stuff alone, the dipole moment does not converge to 0, but it converges to a finite value. But I mean, again, that is since Pierre Bach, we know that. So, okay, this one I want to show. So you can see now, here's an interface. There's a twinning to the left, twinning to the right. Here's again the interface. And now we look at the very high time resolution. We ask ourselves, what is actually this little locomotive which is going forwards and backwards there?
Is this experiment or?
This experiment, yeah. And you can see that you stabilize these kinks. There's just a normal kink in there. Probably I should take my head away here. You can see, I mean, whatever there is the kink configuration, and that kink configuration will completely disappear here because the red has to win over the green. That's the right orientation, that's the wrong orientation, and these ones are the interface. But the important thing is that the interface which is taken out here is the unstable one. So you have here on the top, this material here is stable. This material is not quite stable, but all changes are done by the interface. So you can produce this interface as much as you like. Right? Okay. So the last one I want to show is what happens if you have a simple situation where the strain is running everything. So you have one interface shear to the right, interface shear to the left, and this one gives you the strain. Then the question is are these atomic positions stable or are they unstable? And here you can see already the Eshelby deformation cloud which is there. So the question is how do they change? And the change is then of course by vortices. And here you can see the vortex. So here is your interface. This one is the vortex I was talking about. The vortex remains there and moves from the left to the right because this one is now the transient rotational phase from this part to that part. Right? So everything is there. Yeah, and that's the last one I actually want to show. Here you can see the vortices are unstripped, so you have a vortex where the lattice deformation rotates, and you can rotate to the right and to the left. To the right is green, to the left is red. So if you have two planes, then the vortex would be in between these two planes. But you can have some, instead of twirling to the right, they twirl to the left, and that is what you see here. So you find from the deviation, the undeformed is the uniform. Then in the uniform you have layers. That's the first level of deformation. Then you have a kink in there, and the kinks are responsible for these patterns here. Okay. So at the end, just to show the final graph here. So from these kinks, you can then calculate how common is it to, how fast can these kinks move. Now we have shown that for the last ones I just gave you, they move with the ultrasonic speed, so they're much faster than any other information carriers we have. It's about 3 times the speed of sound. So we can make extremely fast signals which move through the crystal. So I think that's all I wanted to do. Thanks very much.
Thank you very much. Thank you very much for introducing us to all these fascinating phenomena. Questions, comments? Yes.
Yeah, I had a question maybe. In this experiment of controlling the boundary by strain, how important is the temperature of the sample? Is it at room temperature or low temperature?
It's not terribly important, in fact. I mean, it depends where you are. If you're in the athermal regime, which for these movements is about up to 300, 400 degrees, nothing changes. It's too cold. I mean, you have no thermal excitation. But as soon as you have thermal excitation, then of course you get these things.
you have to tell us about the functionality of those materials and the use of these in applications. For doing devices, you need to have the functionality, but also you need to have the capacity to control in a precise way where they appear. And do you have this control here? Can you design a material with the lines and all that in the place you want, or is just the form material they appear wherever they want?
Well, almost. So I mean, the first experiments were always random. So you can make something. You can make a kink. You can make whatever you wanted to do. On the other hand, you can be a bit more specific where you want to do, where you want to go, just by the elements which you're using because they are smaller. And that's, for instance, the kink. The kink is only, you have a plane which is only 1 atomic diameter thick. Now you can say, okay, the entire plane is, I can't tell where I am. I mean, it's somewhere on that plane. But if I have a kink there, that's also 3 or 4 atomic layers thick. Then you can say, okay, it's not just the plane, it's a line on the plane where the kink is. And what we have not done yet is to make the line a point. I mean, you could do that as well, but I mean, that's a block point. I mean, it's the same in magnetism. You have block walls, you have block lines, and you have block points. And we are equivalent to the block lines. The block points are possible. We have published a recipe how to do it, but nobody has done it. So, yeah.
More questions or comments? Okay, so
I have a question, but it's very stupid. Sorry.
I'll do it.
No.
Is there any parallelism with graphene? Because the graphene is also
yeah, it's very thin, yes. And you have similar things in there. But the graphene doesn't twin. So we can't do what we are doing here, but in graphene you can have grain boundary stuff and so forth, and people are looking into that exactly in the same way. So, but there, you have a graphene lattice here and there, and you fix them together so that they're not coherent, and you have an incoherence line. And so that's the equivalent to our twin boundary, but the twin boundary is of course coherent. That's the main difference.
Any other questions? Yes.
You started by showing that one functionality could be as a storage device.
Yes.
And later on you also showed electrical properties.
Yeah.
And people try to bring this together in terms of building resistors, for
Yeah,
example.
with the one as a wire and the other one as yes. Well, there are lots of people working on that, and I think the most advanced area is probably Berkeley. They have about 60 people playing around with this. And there is another one in Australia from Jan Seidel. I don't know how many people he has, but he's very good. So he's looking in various materials. But I should say, magnetism, how many good magnets do we have? I mean, magnet materials, 20, 50, something like that. Ferroelectrics, the same. Now, ferroelastics, the world is ferroelastic. You go into your mountains here, everything is ferroelastic. Feldspars are ferroelastic. Quartz is coelastic, which is sort of a minor version of ferroelastic, but they have also the interfaces. And so it's a very, very common effect. And only in 3 or 4 have we found the functionality, but we have only looked into 10. So 3 or 4 out of 10 is actually not a bad rate. So there might be a lot more. And of course, initially it started more from a chemical side. I thought because the atoms actually are further apart in the interface, just the distance between atoms is about 0.2, bigger. So why not to have new chemical compounds, chemical compounds which otherwise you can't make. So for instance, you take a triangular complex, and in a real material, this triangular complex is always fixed in one orientation, head, tail, tail, something like that. Well, if you have an interface, you have no choice. It either fits that way or it fits that way. And so why not, you have an interface, you go in that part of the interface, in that part of the interface, then one can be okay, but the other one is certainly the opposite. So it doesn't work. So suddenly, when you bring them together, there will be a chemical reaction, but of two constituents, which in the gas phase can never be like that. Because in the gas phase, they will always be in the right orientation. Now you force one of them to be in the wrong orientation. And so, okay, so now to see what can we do there? And, you know, that's one of these big problems we can do.
More questions? I have one stupid theoretical question. In your standard model, you have an underlying lattice there.
Yeah.
Now, what will happen if you have a few long-range interactions so that you destroy the perfect lattice?
Yeah.
Has this been studied or anything on that? Or?
Well, I mean, the heterogeneous lattices, you mean? Yeah, heterogeneous lattices,
I
of course.
was thinking of a small wall type of network and applying I don't know. It's
Oh, I'm sure there's something there. If you take these, for instance, if you have these twinning, so they look like this, and then you can define states by heterogeneous deformation here if you have a kink in there, and these kinks, of course, are then mobile. So that would be a scenario where one can think about. Yeah.
Okay. Thanks very much. Let's thank Professor Salje again.
Okay. Thanks very much. Okay, great.
Okay. I'm glad that you came.
Oh, well.